So in this example problem, we use Castigliano's method to determine all the reaction forces at points A and B. So if we isolate the beam in this problem here, alright, at point A, it has a roller support. So for roller support, we have one reaction force normal to the point of contact. We have our applied load P. Alright, and then at our fixed support, we have our reaction force RB. There would be typically a reaction force along the x direction, but we can set that equal to 0 since there's no externally applied force in this situation. But we also have a moment about point B. Okay, so we have, in this case, we have two equations we can use in statics to help solve for our unknowns. We have the sum of all the forces in the y direction. We can set that equal to 0, and we can sum all the moments about a point. Alright, if we do that, alright, we can set that equal to 0. Alright, so those are our two equations, right? But we have three unknowns. Okay, so because we have more unknowns than the number of equations, this problem would be statically indeterminate, and the order of the indeterminacy would be equal to the number of unknowns that we have minus the number of static equations we can apply. So in this case, we have three unknowns and we have two equations we can apply. Therefore, we have one equation to solve. We need to use one equation to help solve for these unknowns. Okay, so what we're going to do is we're going to treat the reaction force at A as an applied load. So what we're going to pretend is that our loading situation that we have drawn at the top of the section here would be equivalent if we had a cantilever beam where we have our applied load. We're going to treat our reaction at A as an applied load and our applied force at P as an applied load, and then we're going to have our two reaction forces RB and our moment at the cantilever beam. Okay, so we're going to pretend that this is our problem statement, and then we're going to use everything. We're going to rewrite RB and MB as functions of RA and P. Okay, so if we sum all of our forces along the y direction, we should be able to solve for RB. So we should get RB plus RA minus P. Okay, so we can say that RB would be equal to P minus RA. Okay. Alright, and then if we do the same thing, if we sum the moments about point B, and set it equal to 0, what we'll end up getting is we'll get the couple moment at B plus the applied force P times L over 2 plus the reaction force RA, or I should say minus the reaction force RA times L. Okay, so if we rearrange that, we should get MB should be equal to RA L minus P L over 2. Right. Alright. So the second step of the problem is we're going to then determine mz as a function of x. Okay, so in order to do that, we're going to take a couple section cuts here. So we can take a section cut 1, and we can take a section cut 2. Alright, so from x is between 0 and L over 2, if x is 0 here and it's x is equal to 1 at the support, If we take a section cut there, our moment as a function of x, if we sum it about a point, we would get if equal to 0, and we get mz of x minus ra of x. So it would be ra times x. So we should get mz of x would be equal to ra x. All right, and then from x is equal to L over 2 to L, if we did the same thing, if we summed all of our moments at x, instead of equal to 0, we would get mz of x minus ra of x plus p times x minus L over 2. Okay? If we rearrange that equation, what we'll end up getting is we'll get mz of x would be equal to ra x minus p times x minus L over 2. Okay? So we can plug this in to ours. So I guess then the second thing we need to do is we need to take the derivative of mz with respect to our the reaction force Ra. So we're gonna use that. The reason we're going to do this is going to be clear in a second, but for now I just want you to take the derivative of mz with respect to the reaction force at point A. Okay, so if we do that for both of these problems, what we're going to end up with is we're going to end up with from 0 to L over 2 dmz dra would just give us x, and then for the second problem over the second half of the beam, it would also just be equal to x. Okay, so we can then plug this in to our simplified Castigliano's method. So we can say that the displacement at point A would be equal to the derivative of u with respect to the applied force at point A, which is in this case is our reaction force Ra. Alright, so if we do that, we can plug in our terms here. So this is the equation we need to use: 1 over e to the I z, m of z, dmz dra dx. Okay. Now, what we're going to use in order to help solve this problem is we're going to use the boundary conditions that we know for the given loading. So in the situation we have above, we have a roller at point A. Right, we know the displacement at a roller is going to be equal to 0. Okay, so what we can do is we can set this equation here equal to 0. Okay, and by doing that, we can then solve for our unknown force Ra. Okay, in terms of our applied load. All right, so if we do this, what we end up getting is we get our equation ends up being 0 is going to be equal to L over 2, 1 over e to the I z times our moment of z from 0 to L over 2, which is just equal to Ra x times x dx plus L over 2 to L. So we're going to plug in our mz of x terms from L over 2 to x. So if we do that, we will get Ra x minus p of x minus L over 2. That gets multiplied by x dx. Alright? So the rest of the problem is just doing some calculus and algebra. So if you keep going, what we end up getting here is we'll get 0 is going to be equal to RA over e to the iz. Alright, then this term here would just be x squared, so the integral of x squared would just be x cubed over 3 from L over 2 to 0. Our next integral is a little bit more complex, so we'll still have the 1 over e to the iz term. The integral will be from L over 2 to L, and then we'll get, it should be equal to RAX squared minus p x squared plus p L over 2 x, okay, dx. Alright, so if we integrate all those terms and we evaluate this first integral, what we'll end up getting is the first integral just becomes RA over 3 e to the iz times L cubed over 8 minus 0. And then the second term here becomes, our second integral here, we'll keep out the 1 over e to the iz, and then we'll get RA x cubed over 3 minus p x cubed over 3 plus p L x squared over 4. And we have to evaluate that from L to L over 2. Okay, so if we keep going here, we'll get 0. This will be, the first term will be equal to R a length cubed over 24 e to the iz. Alright, the second term here we'll get will be equal to 1 over e to the iz. We'll have RA over 3 times x cubed. If we evaluate x cubed, we'll get the length cubed minus the length cubed over 8 minus p over 3 times that same term. We'll get the length cubed minus the length cubed over 8 plus PL over 4 times the length squared minus the length squared over 4. Alright, so if we keep working on this problem, what we'll end up getting, alright, just copy the first term. Alright, this term here will become 7/8, so we'll get RA, 7RA over 24 minus P, 7P over 24 plus this term here will become L squared, P L cubed over, this would be 3/4, so this would be 3/16. Alright, so what we can do here is we can separate the terms that are functions of P and the terms that are functions of RA. So if we do that, we will get 0 is going to be equal to RA times over e to the iz times the length cubed. Sorry, there should be a length cubed term there and a length cubed term here. Alright, so we get the length cubed over 24 plus 7 over 24 length cubed. Alright, for RA, and then for P, we have to find the common denominator here, so the common denominator is 48, so we'll get plus P length cubed over e to the iz times minus 14 plus 9 over 48. So what we can do now is we can move this term to the other side of the equation. And what we'll end up getting is we get RA times the length cubed over 24 e to the iz is going to be equal to PL cubed over e to the iz times 5 over 48. Okay. So what we'll notice here is that the length cubes will cancel out, the EIZs will cancel out, and we can multiply both sides by 24. And I think I made a mistake. So RA is going to be equal to if you multiply both sides by 24, we'll end up getting 5 over 2 times P. Damn it. Oh wait, I knew I forgot something. Okay, sorry. The real solution is when I took this out, I forgot to add this. There should be an 8 here. Okay, so that'll make our lives a little bit different. This would be equal to 5/16 P. Okay, much better. All right, I knew there was something simple that was forgotten. Okay, so there's our 5/16 P for RA. We could then use our we know that RB is equal to P minus RA from our equilibrium equations. Therefore, it would be equal to 11 over 16 P. And we know that our moment MB would be equal to RA L minus P over 2 L. So we would get 5/16 PL minus 8/16 PL, which is just going to be equal to minus 3/16 PL, which just means that the applied moment would be clockwise. It would be a clockwise moment. Alright, so in short, for solving the statically indeterminate problems, what you need to do is you need to use the boundary conditions of the problem in order to solve for one of the unknown reactions. So in this case, what we could have also done is instead of solving it for at point A, we could have solved for the one of the reaction forces at point B. So what we could have said is that we could have treated the beam as a simply supported beam where we had a whatchamacallit at one end, a roller at one end, and a pin at the other end where we had an applied moment. Okay? So in this case, the boundary condition that we would use is we would say that the slope at point B, which we know is equal to the partial derivative of the strain energy with respect to the moment that's applied at point B, we would set that equal to 0, and using this integral we could solve for what MB would be, and then using MB we could then solve for, with MB we could then solve for the reaction at A and the reaction at B. Okay? So via these types of problems you can use the your unknown forces, you can use the boundary conditions and Castigliano's method in order to solve for the unknown reaction moments and reaction forces within a statically indeterminate problem.